When we think about glass, we usually see it as a brittle material which is easy to break, and so we try to avoid high loads or heavy weights. However, you probably have noticed that nowadays glass is a reliable structural material on which we can even step on with the only risk of fear of heights. These spectacular glass structures are the result of years of research and development of both engineering analysis methods and manufacturing technologies. We know glass is a brittle material, but what does this really mean? Most of the typical engineering materials, such as metals, alloys, and even plastics, are not brittle but ductile. This means we can apply some forces up to some point at which permanent changes of shape take place. These permanent deformations that do not produce breakage or crack growth are called plastic deformations, and they are very useful from the engineering point of view since they suppose an energy dissipation mechanism. For example, in case of an impact, ductile structural components can dissipate the impact energy by producing plastic deformation, and this way avoiding other catastrophic failure modes. Also, since these plastic deformations happen with a reasonable advance with respect to breakage, they are a useful tool to prevent collapse or detect defective structural components. On the other hand, we find brittle materials, such as glass. Because of its random molecular structure, glass is not able to produce permanent deformations without breaking, and so the only available mechanism to dissipate energy is crack growth. Consequently, if we want to understand how brittle materials break, we need to understand how and under which conditions cracks grow. Small defects and cracks produce a sudden change in the local stress field, which may lead to very high stresses. In a ductile material, these high stresses are smoothed by the plastic phenomenon, but they remain high in brittle materials. As a result of this fact, the presence of small cracks or defects is closely related to the load-bearing capability of brittle materials. So, if engineers want to improve their design capability with brittle materials, they need to improve their knowledge about this relation and also about the mechanical behavior of crack bodies. On the other hand, if manufacturers want to improve the load-bearing capabilities of the glass they produce, they will need to find techniques and methods to reduce the number and size of these defects. But which are the most common defects in glass? Basically, we find surface flaws, edge flaws, and inclusions. Typical surface flaws are scratches derived from manufacturing or manipulation. Also, the cutting or machining process leads to edge flaws, which can be highly reduced by edge finishing. According to some researchers, this reduction may lead to an increase of 100% in the effective strength of the material. Typical inclusions are presence of bubbles, crystalline inclusions, and inhomogeneities such as glass inclusions with different composition. These are generally called chords or also striae. Fractal mechanics is the field which analyzes the mechanical behavior of crack bodies. When a crack is present, we generally talk about three different crack growth modes. Mode 1 is the opening mode, typical of surface cracks in components loading bending, for instance. Mode 2 is the shearing or sliding mode, typical under shear loads, but also could be the dominant mode in an inner crack whose plane is parallel to the surface of a glass panel under bending. Mode 3, the tearing mode, is probably the most uncommon in real-life situations. Actually, in many real load cases, cracks are under a mixed opening mode, that is, some combination of the three pure modes. There are specific tests to measure crack opening resistance in the three different modes, even though mode 3 is very hard to reproduce in a laboratory. Also, some tests can measure mixed mode resistance. Generally, mode 1 resistance is smaller than mode 2 and mode 3. So for the sake of simplicity, let's focus on this situation. As mentioned in the introduction, we are interested in the strength of glass as a brittle material, so we will stay within the limits of the so-called linear elastic fractal mechanics. This means the behavior of the material is linear elastic and we do not have plasticity or damage. Under these circumstances, let us imagine we have a glass panel load in tension. If the material was pristine, it would be homogeneously loaded, since internal load lines can connect the applied load and its reaction without any disturbance. The distribution of these load lines, which we can understand as internal forces, would be homogeneous. Since internal forces are responsible for stresses, it's easy to see that the panel will exhibit a homogeneous stress state. Let us now imagine we have the same glass panel, but with a small surface crack of length A. With the presence of the crack, load lines cannot directly connect the load and the reaction, and they have to shift to avoid the crack. Consequently, lots of load lines accumulate in the region close to the crack tip. If we again think of these load lines as something closely related to stresses, the concentration of load lines leads to a larger stress level. At the tip of the crack, the accumulation of load lines is so large that the stresses tend to infinity. As we will see, this happens when the curvature of the crack tip tends to infinity. Since the sharper the crack is, the more difficult to find a trajectory to border it. One of the pioneers of fractal mechanics was Inglis. In 1913, he studied the case of a plate similar to our previous cracked glass panel. In this case, Inglis considered an elliptical hole in an infinite elastic material under a uniaxial remote stress perpendicular to the hole. Of course, we don't have infinitely sized panels, but we can imagine some panel whose dimensions are much larger than the crack length. The interest was to find the local stress sigma A as a function of the remote stress sigma infinity. Inglis derived the following equation. In this expression, A and B are the major and minor radius of the ellipse. So we can see that for a circular hole, that is A equal to B, the local stress sigma A equals 3 times the remote stress. As you may know, this is the maximum value for local stress when stress concentration happens. But according to this equation, the local stress tends to infinity as the ellipse flattens to form a sharp crack, that is, when B tends to 0. This is what we call a stress singularity, and it should not be mistaken for a stress concentration. From Inglis' equation, we find two paradoxes. Paradox number 1, the local stress does not depend on the size of the hole, only on its shape, that is, the ratio A over B. Paradox number 2, for any sharp crack, even a very small load produces failure. According to the equation, if B tends to 0, the local stress goes to infinity, which would mean that even the smaller load causes infinite stresses, which would imply fracture. Of course, we know that glass can withstand large loads, so clearly there is something in this equation which queries traditional stress versus strength analysis and points out the need for other techniques to analyze situations where we have sharp cracks in brittle materials. As a conclusion, we could say that we cannot rely on classical engineering stress versus strength analysis to predict the failure of brittle components, since according to stress analysis, close to the tip of a sharp crack, almost any load would produce breakage. In fact, when regular strength tests are performed on brittle materials, the values of the properties obtained tend to have a large dispersion. This is because the strength of the test specimen is strongly related to the size and shape of its largest defect, more than to the atomic level forces that keep the material together. Modern engineering analysis uses fractal mechanics to predict and design the load-bearing capability of brittle materials such as glass, or quasi-brittle materials such as concrete or composite materials. We will learn about two of the key magnitudes of fractal mechanics analysis, the stress intensity factor and the energy release rate, in another video.